All right, thanks everybody. It's my pleasure to be here once again. My name is Matt Yarnold, current faculty at Texas A&M. So just going to give a few research updates. Two projects listed here, 7112. It's a mouthful, development continuous for live load prefabricated steel ABC unit for Texas bridges. I didn't come up with that name, but it's a good project. I'll spend most of my time there, and then the latter portion will be 7093 refined design methods for lean-on bracing. So starting out with the first project called the Steel ABC project, you can see the objective there. Some of you are familiar with this. Background is kind of shown in the lower right. The Dallas district, probably 3-4 years ago, did their first accelerated bridge construction project where they went with kind of standard approach with two steel girders, prefab deck slab. You see reinforcement coming out in each direction, and it's sort of this was a extended weekend closure superstructure replacement, built, in pieces with longitudinal closure pores and transverse closure pores. At the pier bends, the girders were not made continuous, so it's just simple for dead, simple for live, though there is a standard sort of TxDOT continuous deck slab detail. Through TxDOT, I guess, because this was a project conceived internally at TxDOT, they wanted to look at alternatives to improve the connection at the pier bends to make the girders continuous for live load, maybe improve the performance of the deck slab in that region. Because it's an ABC project, you see sort of the secondary objectives there. We want to come up with a connection detail that's easy to construct, to assemble, durable and safe, cost effective, and so on. So I'm going to go through high level the main tasks and where we are. We completed the first task, had two parts. First is literature review. In this area, there's kind of two camps of prior research and work. First was SDCL. Simple for dead, continuous for live load. It seems like the steel industry, and probably a lot of you familiar years ago, was looking at competing with concrete by going simple for dead, continuous for live load, and sort of short to medium span bridges. So a lot of states had some pilot studies. You can see some work. A lot of work was done in Nebraska, testing in the lab, pilot projects, and so we looked at a lot of different DOTs and state reports on what had been done. And then, of course, there's a lot of research and projects that have been on accelerated construction. And this particular study was where they sort of come together and specifically focusing on the connection at the pier bend region. Shark 2 did a lot of work. The first permutation actually didn't go so well. They had to sort of retrofit their pilot study. And then talking with Iowa, they came up with another project, and they have a whole website dedicated to it where they came up with this detail. I know it's a little hard to see. The steel girders coming together. There's this compression block at the bottom, and then the whole thing, there's this big concrete cast diaphragm at the end. It's still labeled as accelerated bridge construction. Our research team kind of questions how fast it is with this amount of concrete being cast and poured, but this is kind of the latest type of detail that we've been seeing throughout the states. The second part of this kind of fact-finding first task was to do a field assessment of that bridge in Dallas. Here's another shot of it here, them just putting the segments in place. You can see in the lower left, this is a TxDOT material for the way the segments were all put in place and then closed together. So we did a field inspection just to see how, after a couple of years, this first project fared visually, and then we did some targeted monitoring. So I'll give you a summary of the inspection in a moment. The monitoring was pretty small. We decided to put longitudinal displacement gauges, top and bottom, trying to capture the relative rotation at the pier bends, and also installed strain gauges on the girders near the negative moment region, if there is any continuity between the any force couple developing between this continuous slab and the bearings, and then also put some strain gauges out near mid-span, and again, just trying to capture the rotation. We wanted to put strain gauges on the bottom surface of the deck, but the formwork was left in place, and so we didn't have access to the bottom surface there. Just high-level summary, because that's all today really is going to be. The inspection, again, we couldn't access the bottom of the deck, but pretty much every single overhang, and this was a parallel structures, had cracking on the bottom surface of the overhang. You can see it there. They all look like this. So crack propagates all the way through the deck, and it's tough to see, but it wraps around the rail. You can see efflorescence. It's an active crack. We did go out there a day after it rained, and you could see water getting its way through the slab and then around the formwork and collecting on the pier cap. So active cracking at this region. And then the measurements kind of back this up. We were getting the, the girder end rotations from just service, thermal and live load events, and then just using kinematic, just basic geometry, projecting how much strain or stress is in the deck, and you're well above the cracking strain. And this is consistent with the sort of the Texas pour buoy joint detail, which some of you may be familiar with. But anyway, we want to understand kind of what had been done and where we could sort of improve. And the idea is to make this continuous girders, maybe sleek up the design as well as minimizing the deck level cracking, because it's not really a safety concern here, but more improving the sort of long-term serviceability of the structure. All right, so to come up with a new detail, there's kind of 3 parts to connecting spans together in an accelerated way. As far as the deck, that Dallas bridge went with more of a conventional concrete closure pour that's reinforced. It was about 1.5 feet, 2 feet. The other option we were looking at is UHPC, a much narrower closure, maybe even not reinforced, or going with a dry match cast section that would be pre-compressed. I'll show you later. Top of the girder, the standard details that we've been seeing, like out of Nebraska and some other states, don't have a connection to the top flange. It's connection at the bottom to transfer the compression, and then they transfer the tension through the reinforcement in the slab. But we're looking at, I think it's worth exploring connection at the top of the girder with splice plating, post tensioning, whether it be attached to the steel or a thickened slab region and post tensioning off the concrete. And I'll show you what this looks like in a minute. And the bottom of the girder, again, transferring the compression at this location. We're looking at splice plating, some post tensioning ideas, bearing plates and shims, so just a steel transfer, or concrete, but much more confined. And actually, Nebraska is doing a study on this right now where they're looking at like channels welded to the back of the girders and having like a confined concrete region at the bottom there. All right, so if you can see here, there's a lot of ways to sort of mix and match this. We came up with kind of 6 ideas, and then I'll show you, we presented this to a couple of you in the room for an industry review panel to kind of provide some more practical feedback. So I'm just this is high level. These are just done in Google SketchUp. They're just renderings to kind of illustrate concepts. They're not, engineering drawings, and they're animated with videos. Typically here for today, I'm just showing you a static image. Here, our first concept is kind of the most conventional. It's just a splice, standard steel splice plating. There is one on the top of the top flange. You can't see it with the concrete closure in there, but splice plating top, splice plating bottom, and a conventional cast in place closure pour that's reinforced. A lot of feedback on this, or issues potentially with fit up. So we're looking at, if we have to go oversized holes, you have to do some field drilling. Maybe the splice plates are drilled prior and then we field drill the flange. So fit up issues may be a concern with this one. Also, if you look at the bottom of the bottom flange splice plate, do we have enough room to keep the same standard details for the bent caps that TxDOT has without needing additional width, which could be a problem. The second concept, going a little more outside the box, maybe UHPC closure pour, pretty narrow, and then pre-compressing the deck slab with some post-tensioning, also transferring the tension there in the top. So steel bracket assembly on the bottom of the top flange, again, PT bar. So the brackets and everything would come out prefab, same thing with the deck up till the center there. And then you'd have welded plates on the bottom, prefab to the girder. Again, this is not fully detailed, it's just concepts. And then you'd have some, for fit up, be able to put some shim plates in there and either field welded or bolted to stay in place. And then of course, this is more active instead of passive like the last one. So you would pre-compress and keep the deck in net compression such that, you wouldn't have an active crack opening and closing with traffic. So completely different idea, sort of segmental concrete inspired, if I'm allowed to say that in the Steel Quality Council. This is your ultra fast option that one of our research team members came up with. So this is all prefab. You have your girders, and it's like bluish purple on your screen, but you're seeing through the web. So this would come out, it'd have completely precast, and you'd have a concrete end diaphragm and sort of like a blister, so that the deck was thickened. And you can see in the back there would be conduits such that, you erect these segments, they're match cast, kind of like segmental box girders. You probably have a epoxy or whatnot surface between them. And then you would post tension them together. You could put post tension on the bottom as well. But the idea is this would be true ABC, it'd be in and out, kind of like the rail industry. You get in, get out, and replace, the superstructure rather fast. Concept 4 is really similar to 2, except if no UHPC in the deck, more conventional deck, the PT is the same. And then the bottom is kind of what Nebraska is looking at right now. They have an ongoing study looking at transferring the compression instead of doing a big concrete diaphragm like they do, would be almost like built up channels welded to the girders. And then you probably need a bottom plate, but then you would fill it with UHPC and have that confined concrete to transfer the heavy compression at the bottom of the girder. Okay, so 5 and 6, we started getting a little out there. This was an idea someone came up with, these sort of post tension in 2 directions and basically create a couple and induce a moment in the opposite direction to counteract the superimposed, negative bending from traffic and thermal. We'll spend a lot of time on this. This one didn't go over so well, you'll see. And then the 6th one, this is kind of interesting. It was like, okay, how can we pre-compress the deck without using post-tensioning to try and keep it in net compression, minimize the cracking we're seeing? And the idea was, well, if we erect the bridge slightly elevated, right? So this, for our numbers, this was an 80-foot span, three-span continuous bridge. But if you erect it on, say, Enerpac jacks 10 inches high, pour your UHPC, let it gain strength next day. Now, essentially put a support settlement in, you'll pre-compress the deck, and then, you've now, put your deck in net compression, and hopefully long-term serviceability will be improved. There are obviously some constructability concerns with this, but this is a way to try and pre-compress the deck without, steel PT and all that. So that was the other kind of outside the box concept. So everything was sort of on the table at the beginning. We assembled, or I was tasked with assembling the industry review panel. TxDOT internally came up with their 7 individuals, and then I asked people, some of which are in this room. Ronnie was on the panel, and several others to provide feedback on all these different concepts. So we had High Steel, at WAFCO, someone was there. We had NSBA representative there, a steel expert detailer, several designers and people, one person very well versed in ABC. So a decent cross section of the industry to provide feedback, both quantitative and qualitative. So this workshop was held on the 13th of May, and we went through a discussion and kind of evaluated, I call it the benchmark, which was that big concrete cast detail that I showed in the beginning, and then went through each of the 6 concepts I showed you, and they scored, quantitatively, like, 1 to 5, and, just like, doing surveys, but then also had write-in kind of qualitative input on, this is terrible for fit up, or this is great for whatever. And then we had big discussions. We took lots of notes and got a lot of other qualitative feedback. At the end, we had, we call it ideation, not my word, but it's sort of like a brainstorming session to say, like, to the industry, like, is there anything else we're missing? Any other ideas you have? In the end, it came down to, let's just compare this to a link slab and see the pros and cons between the two. So high level summary, as we went through each concept, the members scored in those areas. So ease of fabrication, ease/speed of assembly, structural performance, like initial costs for construction, maybe projecting long-term, costs and maintenance. And so they scored all of these. Right now, this is just showing if they're all equally weighted and you total them all up. Concept number 3, the segmental inspired actually rose to the top, which was really surprising to us. And the 2nd and 3rd were the 2 that have just the steel PT up at the top. And this was, and you can see in the graph here, the orange is industry and the blue is TxDOT. Both kind of had pretty consistent results. We then went to the end of the workshop and had this big sort of summary session where now people had seen all the details and weighed in and said, okay, if you were to build this thing, next year, what would you want to do? The conventional splice plating leapfrogged everything, and that became the first alternative, which I thought was interesting. The segmental inspired one, and everything really just dropped down a peg, and you could just see the other 2 alternatives there. And the last piece of workshop feedback I'll share was we then said, okay, what if you just evaluated each sort of connection separately? So if you just wanted to splice the deck together, what would you prefer? It was regular, concrete closure pour seemed to make sense to be the preferred alternative. We can get that to work. UHP second, which wasn't far behind. Seems like people are more accepting of UHPC these days, but not so much match casting. A lot of concerns on field fit up with match cast. The top of the steel connecting it was kind of level, if you see there in the middle. Not a huge preference, although steel splice plating was preferred. And then as far as the bottom, there were three that kind of stuck out. The splice plating, the middle there in yellow, bearing, just conventional bearing plates, just have steel transferring the compression. And then the third one was confined concrete with UHPC. So we got that. We also got a lot of other feedback from TxDOT and people TxDOT construction experience, and came up with these four essentially. They're oriented this way because in our contract we're supposed to carry through three. We have to do, I think, I relabeled them here. A is the steel splice plating alternative, so we're going to test that out. The second and the third there, B and C, some of the feedback we had was if you're going to do UHPC and you're going to mobilize in the field, doing UHPC, might as well do it in full. So don't have it just in the deck or just in the bottom. So we're going to do that concept B, and that's why I have the arrows. It's basically to have like a UHPC closure in the deck and then UHPC at the bottom with steel PT. And then that third concept will just be more conventional concrete in the deck and then just conventional steel plating to transfer the compression. We want to try and include this. It scored pretty well in certain areas, that segmental inspired concept, though there was a lot of concerns on fit up, particularly with, the elevations and things we deal with. So we're looking at maybe a modified detail with a grouted closure for D. And there's a caveat there. We're originally supposed to do three. So we're going to try and do a fourth if we can. It's kind of the idea with time and resources. So. Where we are now is putting together drawings to get the steel fabricated. So that should hopefully go out relatively soon. And then this is an old sort of rendering. We're basically pulling out full scale from the inflection points of the bridge. So, the pure bent region, these will probably be about 20-foot girders, and we'll probably just tie down the one side and then just load off the other. We'll do surface level cyclic loading, kind of look at, crack initiation, crack propagations in the deck, surface level performance, and then we'll incrementally load it up to failure and look at the failure mechanism and whatnot. We'll do this for 3 or 4 of these, take everything learned from the sort of structural performance along with all the fabricator, erector, contractor feedback that we got from the workshop, and then come up with some standard details, specifications, and then design examples for TxDOT engineers if they so choose to adopt this. All right, so that was Steel ABC project very briefly. Now, refined design methods for lean-on bracing. We already heard about, the lean-on bracing, and NSB has put out a guide. We also have so obviously a second project. The initial projects done at UT many years ago, and there's a desire within TxDOT to kind of refine things and improve some of the design expressions, as well as provide guidelines for sort of the layout and recommendations just in general for lean-on bracing applications. I don't think I really need to explain this to this group, but I went back and forth on this. What is, lean-on bracing, just in case we don't miss anybody. There's conventional, steel girder bridge, typically brace in every bay. Here's just cross X bracing for lean-on bracing, typically bracing, 1 or maybe 2 bays. And then this is kind of taking a page out of the building industry of using leaning columns. You sort of lean all the girders off of that brace bay with just a top and bottom strut. And kind of the motivation is to reduce all the extra cost and time associated with, fabricating more and more cross frames. Background on this is a shared project. UT is taking the lead. Todd Hellwig's not here yet. It's coming in soon. But it's a partner project. Dr. Hellwig's the overall PI, and I'm leading the effort from A&M, and then I'm in the process of subcontracting to Auburn. But we meet weekly, and this has been kind of pleasure to work on so far. But all questions go to Dr. Hellwig. Tasks 1 and 2, just real high level. I think I'm doing good on time, and I'm told to make sure I don't finish too early because Dr. Hellwig's not here yet. Tasks 1 and 2, kind of fact finding. A lot had been done internally, on the team. Dr. Hellwig, Dr. Englehart's on the project. So reviewing the literature, seeing what else is out there, and then recent bridge designs, kind of going through. The big one in the background for this study, SH-105. I know Jamie had worked on this. I think David, you worked on it. Over the Brazos River. So that was a recently designed and built bridge in the state of Texas. We wanted to obviously go through that. And then another one we found was Chisholm Trail. This is an NTTA bridge. So we met with the owner, we met with NTTA, we met with the engineering firm and designers of the structure. So went through, existing designs, and then moved into kind of field studies. We wanted to get a bridge in construction, but with the timing of the project, you know, SH 105 had just completed, wasn't in service yet, but had just been completed. So we had to do our field studies on completed structures. So the first one was the SH 105 bridge. It's up to see there. This is just the framing plan with showing where our instrumentation was. We instrumented 2 basic cross sections of the bridge, instrumented the cross frames, every member, 4 strain gauges each, and then the top and bottom strut in the lean-on bays. There's just us out in the field. You see we 2 man lifts and instrument the bridge. That's David right there, just showing he's working hard for his master's degree. He was on the project, and so it was a lot of work. We got a lot of really good data that from we did actual load testing. This bridge was not in service yet, and we use that data to then basically validate the final modeling methodology that we're using for the very large parametric study that I'll talk about in a minute. So we also did a parallel effort on the Chisholm Trail bridge. NCTA was nice enough to give us access. This was nice because now that was a straight bridge, no skew. This is 45-degree skew, K-frames, heavy application of lean on. You see there the bold being the lean on, not a lot of cross frames. They took out a large percentage, mostly lean on bays. So gave us another, data set that's really valuable. Again, we just finished doing a lot of modeling and validation for this big 6 task, which we're right in the thick of it. So I don't have a lot to, as far as results yet, but basically we're evaluating different span lengths and skew angle, basic geometry, and then of course looking at different cross frame and lean on layouts to provide kind of guidelines to the industry and specifically to TxDOT. All funnels into the next task of developing enhanced. Some of the design expressions or equations were developed with some assumptions that we'd like to expand, like maybe one bay had cross frames and all the rest had top and bottom struts, but making it more adaptable for multiple bays with lean on bracing and so on. And then also providing a few fully worked out design examples for future TxDOT engineers. So I think I messed up and I finished 5 minutes early. I don't think he's here yet, but I can field questions now if you want, or we can wait. Sure. Except for the highway questions, I guess.
Yeah. Any questions?
Or we can move on to another subject. Yeah.
On the ABC construction, the continuous live load, that bottom connection of the splice plate, like angle bolted onto it.
Yeah.
I think it was.
Yeah.
Why is it going up the left?
So that was, we saw a similar detail. So you're saying just doing the flange, right? I think we're running the numbers. We need a little bit, grab onto a little bit more. I thought it was engage, not just the flange. We wanted to give the bottom push the web, just tie it all together a little bit tighter. Make it a little bit more robust connection. I mean, you may be able to design and get away with just the flanges. That could be the case, but yeah, it's a good point. You may be able to eliminate that piece. You're just trying to simplify it, obviously, right?
Right.
That's a good point. It's a tricky spot to splice things together, we're finding.